we're going to talk about mean and standard deviation and the significance of standard deviation. So let's start with our definition of mean. In a series of experimental values, the mean would be the average or the central value for the set of measured values, with the formula for mean represented by x bar, where it is the sum of the experimental values obtained over the number or numbers of experimental values that are obtained. So this is our formula for the average or the mean value, and the mean or average value, in the absence of a true or accepted value, can be used as a central value for a set of measurements. So for example, in our definition of precision, we talked about the closeness of experimental values to a central value. So what I'm going to do is I'm just going to draw a quick sketch of a bell-shaped curve, where our bell-shaped curve represents a series of experimental values or our replicate experiments or measurements, where we say that the central or mean value will be represented here, and the replicate measurements are found on either side of our mean, such that the mean is the central value for the set of measurements. And this is what we refer to as a symmetrical distribution of values. Keep in mind that when you calculate mean for a set of experimental values, it should also have a unit. We're going to go on to look at standard deviation, and standard deviation uses the mean or central value, which you can now calculate. Let's look at a definition for standard deviation, which is based off of the formula for standard deviation. It is said that standard deviation, represented by the letter S, is a series of measurements where, it is equal to the square root of the sum of the squares of the deviations for each measurement from the average or central value divided by one less than the number of measurements. So I'm just going to write out our formula for standard deviation. In a question, you're going to be given the formula. You just need to know how to apply it, and you apply by being able to work out the mean, and from this formula, being able to work out standard deviation, you can now reflect on the precision of the experiment, where the significance of the standard deviation is that a low standard deviation would indicate a high precision, and a high standard deviation will indicate a low precision. I'm going to use the Bell distribution curve to show what low and high standard deviation means. So if we have our experimental values which are close together in a small range like this, clustered around the mean, that indicates that the standard deviation is small. So it's a small standard deviation, which would indicate a high precision. And that means we have values which are close together around a central value. So that should also mean that there is a low amount of random error in our experiment, or a low amount of experimental error, where we have a flattened curve. That is, our experimental values are spread apart around the mean. We have a high standard deviation, And this high standard deviation will indicate that there is a lot of experimental error or random error, such that we have a low precision in our experiment because of the lack of closeness between our experimental values. So let's look at a question which applies mean and standard deviation. You are told that 4 students performed titrations, and from the titer values obtained, the students calculated a mean value, and from the mean values, they calculated their standard deviation. You are asked to comment on the accuracy and the precision of the data obtained, meaning you have to comment, is it accurate, not accurate, precise, or not precise. So we're going to start with our standard deviation, having gone through it before. And you are told a small standard deviation means a high precision. So we're going to look at our values here, and we have a 0.03. So this student would be precise. And we also have a value of 0.06. So we can also state that this student is precise as well because of how small the values are. And if we look at the differences in the standard deviation, which tells us that a student is precise compared to the other values, which are about like 100% and more than the smallest value, this will indicate that 1.15 and 3.46 are very large compared to our values, which indicate that the student was precise. So in looking at these two values here, we can say that these two students were not precise because of how high the standard deviation is. We've commented on the precision. Now let's look at the accuracy, where accuracy looks at the closeness of the experimental values to the true or accepted value. Now you are given the mean, and in a titration, the true or accepted value will be the value that most students obtain, and that value tends to be the central value for a set of measurements. So usually in a titration, your value might center around 25.00, and coincidentally, in these experimental values, we see that more than one student got 25.00 as their central value, which we are going to use as our true and accepted value. Therefore, that means student 2 and 4, we are going to say that they were both accurate. And let's look at student 1 and 3 in terms of how close were their mean values to the central value. Because they are not close to the central value of 25.00, let's say for example student 3, which had a value or a mean of 28.78, we can definitely say that this student was not accurate. This mean value of 24.13 is also not close to the accepted or true value, which is 25.00. So this student was also not accurate. In answering these questions, you're not allowed to use the same type of description for another set of experimental values. So for example, student 1, precise but not accurate. Student 2, not precise but accurate. Student 3, neither precise nor accurate. Student 4, precise and accurate.